Okay, got that going. Let's quickly remind ourselves about what we covered last week. Last week we were focused on validity, right? Well, first off, interpretation. Before we had sentential interpretation, last week we finally gave you a general notion of just interpretation, what it means in general. And then prior to last week, I told you that anytime we prove something, like in the context of a math class, what we do is we show that some implication is a tautological implication, and that was a lie. What do we actually prove? When we prove something, when we give a derivation, what do we demonstrate?
That it's universally valid.
That it's universally valid. So if it's a tautology, then it's universally valid, but the converse is not necessarily the case. Intuitively, what does it mean for it to be a tautology? Basically, we can check it with a truth table of some sort. And so not everything that's true can be checked with the truth table. And so we have this notion of it's universally valid. So if it's a tautology, it's universally valid, but the converse is not necessarily the case. And universally valid meant it's true in every interpretation on every non-empty domain. Remember that the domain had to be non-empty. And then we talked about a bunch of concepts that we already talked about in chapter 2, but just using interpretation rather than sentential interpretation. And then finally, we got to the interesting stuff right at the end, talking about logic as a whole. It's often referred to, what we're covering, most people would refer to as first order logic. So we showed, well, we didn't show, but we talked about how first order logic as a whole, FOL, is first of all consistent. What does it mean for first order logic to be consistent? It means that there are no contradictions permitted in the system. It is impossible for me to prove some theorem of logic that contradicts some other theorem of logic. Provably. We know it's consistent. The second thing we know is that it is complete. What does it mean for it to be complete? Remember? Everything that's true in the system can be proven to be true in the system, which you would expect. How would you know something's true in the system if you can't prove it to be true? And then the one that was a little bit weird is that we showed, well, we didn't show, but we talked about how it's undecidable as opposed to decidable. What does it mean for it to be undecidable?
Can't find an example where it's false.
No, undecidable is that there is no... So going back to with the truth table, if I gave you some expression from just propositional logic, you could always and forever check, is it a tautology just with the truth table? Brute force, go through it.
Right.
Is there something similar for just proofs in first order logic in general? Is there some procedure that if we just follow this procedure, some algorithm, would it be possible for me to construct some algorithm on a computer such that given some formula, it can always check, yes, that is true in our logic, or no, that's not true in our logic. Does such a thing exist? And provably, no. Such a thing does not exist. That's what we mean by it's undecidable. Now, we use first order logic to create axiomatic systems of mathematics. And so then we went on to talk about similar concept, but this time in math. Particularly in arithmetic or anything logically equivalent to arithmetic, which is pretty much everything you think of when you think of a body of math. For example, Euclidean geometry is definitely included. And we asked some similar questions. So first off, is math decidable? If I give you something in arithmetic, is it possible, some statement in arithmetic, is it possible to create some computer program that can check, yes, that's provable in arithmetic, or no, it's not provable in arithmetic?
Yes.
And the answer is no such thing exists. It's undecidable. Because the reason it's undecidable, it inherits that undecidability from first order logic. If this were decidable, everything that's true in math is true for sure in logic. So if this were decidable, and I could come up with an algorithm to check everything here, I could use that same algorithm to check everything here. Because everything that's true in logic is also true in math. The converse is not the case. You can always use logic for doing your math. So it inherits that undecidability from first order logic. So we know any system in mathematics is undecidable.
Isn't there an algorithm that can check that everything is accurate for math?
No. But what we mean here is that, give me some statement we want to check. So we talked about last time the twin prime conjecture. So write out our numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc. One of the open questions in math right now, so twin primes are two primes separated by a single number. So 3 and 5 are twin primes because they're separated by a single number. 5 and 7 are twin primes because they're separated by a single number. 11, 12, 13. 13 and 11 are twin primes because they're separated by a single number. One of the open questions is, are there an infinite number of twin primes? That's an open question in math. We do not know the answer to that question right now. What we mean by math is undecidable is there couldn't be some advanced program that you go out and create, and I can ask that advanced program any question I want, and it always be able to tell me the answer. I can't just ask it, hey, is the twin prime conjecture true? And have it tell me yes, and then give it something else, and have it in general know how to answer those questions. It might be able to answer a very specific question, but there is no general algorithm, there is no general procedure that can just do these things, even with an infinite amount of time. Doesn't work. That's what we mean by math is undecidable, and by logic is undecidable. Since math inherits all of logic, it inherits that undecidability. Because everything that's true in logic is true in math. And so if there were something I could check all the things I want to know are true in math, I could check those same things in logic.
So we're proving that, the undecidable feature, function, property, trait of first order logic is true, and didn't last class we use math to prove that was the case?
So I gave you an example of the simplest undecidable problem that there is, which is the halting problem. And doing an analysis of undecidability is really a topic of computation theory. It's not a topic of logic, per se, although the two are pretty closely related.
I can't remember the guy's name, but he basically somehow converted logical statements into massive numbers.
So that was Gödel
Yeah.
in arithmetic. So that was dealing with this next one, complete.
Yeah, but why is he using mathematics to try to prove something in logic?
He wasn't.
Oh,
He was using mathematics to try and prove things in mathematics.
only mathematics.
Only systems of math.
Gotcha. Okay.
So then the next question was, is math, like arithmetic, complete? Just like it is in logic. What does it mean to be complete? That means if it's true, then there's a proof that's true. And the big shock to the world is what Gödel proved, and he proved that this is incomplete. The shocking part about that isn't not only that it's incomplete. So there are true statements in arithmetic that we can never prove to be true. Not it's really, 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 really hard. There are true statements out there that just flat out can't be proven to be true. Period. The most shocking thing about what Gödel did isn't just showing that it's incomplete. He did this by finding a true statement that cannot be proven to be true in the system. Now, why is this so shocking? Because we human beings understand that the statement is true, even though the statement is impossible to prove. And so this shows that there is a very big difference between something being provable versus it being true. If something's provable, it's obviously true, but just because something's true doesn't mean it's provable.
That sounds like it's just intuitive if you can't prove it.
Well, I wouldn't call it intuitive, but yes, human understanding. Whatever human understanding is, it goes beyond proof. We can understand things to be true that it is impossible to prove that they're true. Absolutely shocking.
It doesn't seem like it's in line with the rules of logic.
Right, it seems very strange, very weird. And we're able to go outside, our human understanding is able to go outside of systems to perform an analysis on that system. So we know things are true in the system, that it is impossible to prove that they're true in the system. There's no way to derive it from the axioms. Absolutely shocking.
Which indicates that maybe there's the approach of proving is incomplete.
Maybe the approach of proving is incomplete, but if our approach of proving is incomplete, our approach to physics is incomplete. And so our approach to chemistry is incomplete. And so our approach to biology is incomplete. There's kind of this simple-minded notion that all human understanding is really just activity in the brain. And all activity in the brain is really just chemistry. And all chemistry is really just physics. And all physics is ultimately axiomatic systems that describe our universe. And yet, human understanding can know things that it's impossible to prove in the axiomatic system. So wherever the laws of physics are, they're for sure complex enough to encode arithmetic. That's for sure. And so, incompleteness theorem applies to whatever axiomatic system we would ultimately encode laws of physics in. If there were these perfect equations that could describe everything that happened in the universe, including humans, then they would perfectly describe human understanding. And so everything humans can understand would be derivable from those axioms. But provably, there's things that we can understand that aren't derivable from those axioms. Completely shocking. In no way intuitive. But that's what it says. And then finally, okay, is math at least consistent? We better have this one. Because if math is inconsistent, that means that you can prove a contradiction. Yeah. And what Gödel proved is that if math is inconsistent, it's impossible to prove it's consistent. Or sorry, if math is consistent, it's impossible to prove it's consistent. So is it consistent? Everybody kind of assumes it is. But all we know is that if it is consistent, it's impossible to prove. If it's inconsistent, we can prove that. We just derive a contradiction. If we ever find a contradiction in math, we're done. It's inconsistent.
Isn't that just because it's also incomplete?
Well, these two are very related to each other.
It just seems like if something is incomplete, then there's no way to prove that it's consistent.
Right.
They're very related topics. Yes. And so, if it's consistent, it's impossible to prove it's consistent. So that was some of the big picture things we talked about last time. Now, for today, we're going back down to just our next rules of derivation. And now we're going to start working with the existential quantifier. So let's remind ourselves now of our rules of derivation. What are the rules of derivation we have so far? When we're doing a proof, what are the rules we can use?
You can have a conditional premise.
CP, that's kind of one down there. So first off, we can introduce a premise at any point. Rule P. Then we can introduce a conditional premise, a premise that we can later get rid of.
Tautology as well?
Yes, rule T, meaning we can use any tautologies out there. Any rules of logic we're allowed to use in our derivations. So this is what enables us to use something like not alpha or beta, gives us, I don't know why I did A instead of alpha, gives us not alpha and not beta. That's something we show with the truth table. This T is what says we can use that. So rule T basically says everything you showed is tautology with the truth table, you can go ahead and use it. Okay, what other rules do we have?
We can introduce contradictions.
Yeah, reductio ad absurdum, proof by contradiction. Okay. And then we had our two rules for working with universal quantifiers.
Yeah.
So that was universal specification. That's a rule for when we get rid of a universal quantifier. And then finally we had universal generalization, which is our rule for adding back a quantifier. We only have two more rules of derivation left, and then we're done with all our rules of derivation. And the last two rules are going to be existential specification and existential generalization. Our rules for removing existential quantifiers and our rule for adding on existential quantifiers. And then we're done. And that's all our rules of logic. With me? So let's go over them. So before we go over the rules for existential specification, existential generalization, let me give you the intuition or the idea behind the rule. Here's the idea behind the rule. The assertion that there is something satisfying a given condition implies that the given condition is satisfied by some nameable individual thing, or some constant. If it sounds like I'm basically saying the same thing twice, that's kind of how it should feel. The assertion that there is something satisfying a given condition implies that the given condition is satisfied by some nameable individual. And conversely. So if we can find something that is satisfied by some nameable individual, then we can conclude that there is something out there that satisfies the condition. Let's see some concrete examples. If I know that there exists something out there, such that it's human, then I can conclude that human applies to some particular person out there. Now, we put John Doe here. Why are we putting John Doe there? Because we don't know who that particular person is. If I tell you that there exists something out there that's a human, then you know that there must be some person out there, some individual person. You might not know their name, but, so we use John Doe, such that that person is human. Now this is called an ambiguous name. Just because we know that someone satisfies it, doesn't necessarily mean we know what their name is. Let me give you a concrete example. Let's say I tell you that there exists someone in this classroom over 6 feet tall. You can now conclude that there's some person in here, some individual person, such that they're over 6 feet tall. Now you might not know this partly. You might not even know his name. But you know that there is an individual particular thing that satisfies it. Some nameable thing. It's possible to name them. And if you don't know what their name is, we give them some generic name, John Doe. Make sense? Another concrete example. Here's how we'll typically use it in proofs. If I know that there exists something out there such that it's greater than 2, then I can say that there is some particular number, call it beta, greater than 2. So now beta is some particular number. Which number? I don't know. I just grabbed one out of there, and now I've got it. And I'm not sure which one I grabbed.
How is this different than universal specification?
Universal specification is we replace the variable with any term including variables. This is not a variable. It is an individual particular thing that we don't know the name of. A variable is a stand-in for any object. An ambiguous name names one and only one object. It's just an object whose name we don't know.
Those are so close.
They are so closely related, and unfortunately in math, half the time that we come across these things, we use variables to mark them anyways and go on our merry way. And it's just because of the way that we're reasoning, we never make mistakes. Because we know when we're cheating, and so we don't accidentally break the rules. But they're technically different. Okay, and then finally, what does this say? It says that if I know some condition is true for some nameable constant, then there must exist something out there that makes it true. So if I know that 16 is greater than 2, I'm able to conclude that there exists an x such that x is greater than 2. So I'll say this one more time. What's the idea? The assertion that there is something, you can think about that as that's what we're saying there exists x. The assertion that there is something satisfying a given condition implies that the given condition is satisfied by some nameable individual or a constant. And vice versa. If it's satisfied by some nameable individual, then there must exist something that satisfies it. That's going to be the basic thinking underlining these two rules. You with me so far?
I just can't see how this is different than a variable.
Okay, yes. So, ambiguous names. Ambiguous names, what do they do? An ambiguous name, it signifies a constant whose name we don't know. Variables versus ambiguous names. A variable stands for any object in our domain of discourse. X stands for any object in our domain of discourse when we're using it as a variable. An ambiguous name stands for some particular object in our domain of discourse. One that we may or may not know the name of. Give you an example. I tell you that y equals 6x minus 17 is a line. Here's a line. In this equation, x and y are variables. You can plug in any number x right there that you want and get a corresponding y, or you can plug in any y you want and get a corresponding x. You with me?
Yeah, I do.
So now I say, now I'm going to pick a point on that line. Now that point, this, is an ambiguous name. Pick a point x1, y1. That is now a point on the line. This isn't talking about all the points on the line. This was something that was true for all the points on the line. This is now a particular point on the line. Which point? We don't know. But it's one of them.
Single value.
It's some particular point. It's out there. And we just don't know the name of it. Or we could have picked a point on the line whose name we actually knew. So for example, let me see, if I plug in 3 for x, then 18 minus 17 is 1. We get y for 1. So 3, 1, there's a point on the line. There's one we know the name of.
So it's not ambiguous anymore.
So this is not ambiguous. This is a constant, but it's a named constant.
Couldn't you have done
This is an ambiguously named constant.
Couldn't you have done that same procedure with a variable as well?
Yes.
This x here is not a stand-in for a particular value. It's a stand-in for any particular value.
Such that y equals 6x minus 17. With those conditions.
Right, so this is stating a relationship between two variables. You can plug in any numbers you want as long as they satisfy this. This is now a particular point the same way that this is. This one we knew the name of, it's one and only 1 point. This one we don't know the name of, it's still one and only 1 point. We just don't know the name of it.
So you're saying we're kind of cheating in mathematics when we just replace.
We're lazy in naming things. We don't really cheat. Your reason won't let you. If I were to start out with, what would be a simple example? Let x and y be even. So let x and y, e for even. Let x and y be even, dot, dot, dot. Therefore, x plus y is even. And so, in this case, you know that those were variables representing any two even numbers. And I proved then their sum is even. So if I show for any two even numbers you choose, then their sum is even.
Okay.
Now I might have said, here's where we aren't being super bad in math. You tell me that there is some number out there that's both prime and even, right?
Both odd and even.
Both prime and even. So it's 2, but let's pretend we don't know that. So let's say, let x, such that x is even and prime applies to x. Then I might be tempted by that to say, therefore, everything that's even is prime. And you know what? You can't do that, because this wasn't talking about everything even. It was talking about one thing that was even. And your thinking automatically stops you from doing that.
Okay, so we kind of shortcut, and it's like two interpretations of a single statement, essentially.
It's just that we are imprecise in our mathematical proofs, and we rely on our intuition to stop us from breaking rules that aren't made explicit. That's all it is. In logic, we have to make it explicit. So, what are our rules now? And I think we're ready for it. If a formula S results from a formula R by substituting for every free occurrence of a variable x in R some ambiguous name, which has not yet been used in the derivation, then S is derivable from there exists x such that R. So we'll say that again, but first let me show the concrete example. Up there, R could be something like this. S is going to be something like this. We are going to derive from there exists an x such that some formula about x, like x is greater than 2. And we're going to derive from that something like beta is greater than 2. For some beta out there. So let's read this one more time. If a formula S results from a formula R, notice that R doesn't include the quantifier. S results from R by replacing a free variable in R. Notice that x is free in R. It's not free in this whole thing, it's free in R. We're intentionally excluding the quantifier. So S results from R by replacing some free occurrence of a variable x in R with some ambiguous name, beta, which has not been previously used in the derivation. So if that's the case, then we can say S is derivable from there exists x such that R. So here's our there exists x such that R, here's our S. That's how we get rid of existential quantifiers.
So
The thinking is that if we know that there exists some x out there such that x is greater than 2, then we can say that there is some particular thing, beta. I don't know which number it is, but it's no longer a variable. It is an actual number. And since I don't know which number it is, I'm calling it beta.
So we use these rules to basically remove the exists.
To remove the existential quantifier.
Is it just
Existential specification specifies the particular thing that we're talking about.
So could we put for all x, x is greater than 2, and still pull out a single one? That would also work.
Well, let's not mix universal quantifiers in here yet.
So universal quantifiers are for all x's and existential specification or
Existential quantifier is there exists.
okay.
Universal is for all.
That makes a lot more sense.
Okay.
This is all good coming up.
All right. And then finally, our rule for existential generalization. This is our rule now for adding on the quantifier. This was a rule for getting rid of the quantifier. Now we're going to go for the rule for tacking on the quantifier. In this case, our R is going to look like this, and our S is going to look like this. And what are we going to do? We're going to replace our constant or our ambiguously named thing with some variable, then add the quantifier. That's essentially all it's going to say. So if a formula S results from a formula R, by substituting a variable x for every occurrence of a name or a constant, going from here to here, I'm replacing beta with x. Going from here to here, this one says even applies to 2 and prime applies to 2. If I know even applies to 2 and prime applies to 2, I can conclude from that there exists something out there such that it's even and it's prime. So here's our R for this formula, giving you 2 examples of it, and here's our S for this formula. All right, so I'll say this one more time. If a formula S, just that part without the quantifier, results from a formula R by substituting a variable x for every occurrence of some name or some constant. In this case, replace all my 2's with x. In this case, replace all my betas with x. Then there exists x such that S is derivable from R alone. If I can find some particular thing that's true for, then I can conclude there exists some x out there such that it's true. And you don't have to know the name of the thing to existentially generalize. You just have to know that it is, in fact, the named thing. If we had a dead person in this room and we called him John Doe, we don't really know his name. We don't need to know his name to conclude there exists someone in this room that's dead. We can still conclude that. And if we knew his name is Pete, then fine. We now know his name. Doesn't change it. Good so far? Okay. Bad example. What was the bad example I had in mind? Oh, what would happen if we just treated these things like variables? Here would be the problem. Let's pretend that H here is human. So let's start with our premise that there exists something out there such that it's human. If undergoing existential specification, I then replace this with something like H sub x or y, doesn't matter if we switch the variable, then I can now universally generalize on that thing and say, oh, so then for all y, human applies to y. And so this tells me if something's human, then everything's human,
How do we know?
which is obviously false. This was a bad derivation. I do not, when I existentially specify, when I use existential specification, I have to replace that with an ambiguously named constant, not a variable. So I have to replace that with something like alpha. And now, we can't apply universal generalization. Universal generalization only applies to variables. That's not a variable, that's a constant. It's just one we don't know the name of.
Is that like a Greek variable? Is that right?
Oh, sorry. Should specify this notation, yes. Anytime we are talking about ambiguous names, I will use Greek variables. I will use letters at the start of the alphabet for constants, like A, B, and C. And I'll use letters at the end of the alphabet for variables, like X, Y, and Z. And I will use Greek letters now for ambiguously named constants. Constants that we don't know the name of.
Okay.
So this says John Doe is human. If I wanted to say Adam is human, I would just do H, little a like that. That says Adam is human.
Gotcha.
So, yeah, thank you. Meant to explain that notation. Why I'm using Greek letters now. And I'll try to typically use betas, because too often my alphas look like an X, unless I'm really thinking about it. Alright, so with that, let's start doing some proofs. Okay, so our first proof. All humans are mortal. There are humans. Therefore, there are mortals. Step 1. You're telling me.
For all x, if x is a human.
So, can I grab a bad piece of chalk? Or is it just this part of the board?
It's the bad part of the board.
For all x, what?
Given x is a human.
If human applies to x,
Then mortal.
That applies to mortal.
then mortal applies to x. Good. Right? What rule are we using?
A premise.
Rule P. And then finally, this is only dependent upon itself for its validity. My idea of derivations. Okay. What's our second premise?
There exists x such that x is a human.
So there exists some x such that what?
X is a human.
Human applies to x. Okay? That was our premise, and it is only dependent upon 2 for its validity. Okay, now what?
Well, our conclusion is
Let's scribble our conclusion up here somewhere. We want to say, therefore, there are mortals.
therefore there exists an x such that x is immortal.
There exists x such that mortal applies to x. Okay, that's what we're trying to get. Alright, so we've got these two. What now?
We gotta do, I mentioned existential specification and universal specification.
Yeah, so what should we do first?
Just existential specification.
Existential specification. And order here definitely matters. We're going to see why it matters. So we're going to existentially specify it there. We know there exists something out there that's human. We're going to call it Bob, or Frank, or whatever. Some ambiguously named thing. Beta. Oops. So now I know human applies to beta. Beta is an ambiguous name. There is something out there that's human. I'm not sure what his name is, but beta. Okay, now what? Now we universally specify on this. And when you universally specify, you can replace your variables with any term you want. Doesn't matter how crazy or convoluted it is. And so we can replace it with beta. That's just a term. And so if I know it's the case for all x that this holds, then it's true for beta, whoever that beta is.
And we, is it just to our advantage to do
Oh, sorry, this was existential specification, and it was only dependent upon 2. Well, that's ultimately what we want to say. We want to say, since beta here is a human, then beta's mortal. That's ultimately what we're out to say, right?
Yeah.
And so, I now can conclude that if beta is an H, then mortal applies to beta. This is using universal specification on line 1. All right, now what?
Well, if H and B is true, then MB is true.
And beta. So I can just conclude beta is mortal. This was tautologically implied by 3 and 4. And now it is dependent on premises 1 and 2. And now what can I do?
I guess we would do existential generalization.
Existential generalization. So now, if M is true for something out there, then I know that there exists some X such that that thing is true. And that was not universal. That was existential generalization on line 5. And we are only dependent upon premises 1 and 2 for our validity. So we showed that this was entailed by those 2 lines, which were our premises in that statement. That completes the proof, right? Square box. Any questions on that?
Are we at the point where we use domains at all, or is that still kind of a thing you'll teach?
A domain only matters when you're talking about an interpretation. Logic itself couldn't care less about the domain. Logic doesn't care if you're talking about real numbers or if you're talking about geometric figures or what you're talking about. Math does. So when we set up a system of math, we're always talking about the domain that we care about.
I just,
Well, kind of.
well, does this imply that we're using a domain that are of just humans?
All we know, no, not really. This was an interpretation of this. Or sorry, the logic encoded in here is right here. Right? we showed that these symbols entail this. This is one interpretation of the fact that these entail this. These entailing this is universally valid. You can replace H there with any predicate you want, and M with any predicate you want. And you can pick any domain of interpretation you want as long as it's not empty, and the argument will still hold.
Right. Using that second statement, there are humans. It's essential if the domain is just whatever.
But I could say, so humans here is completely irrelevant. Let me come up with another one. All foo are bar. There are foos. Therefore, there are bars. And I can mean H means you're a foo, and M means you're a bar. And this is still perfectly valid.
Yeah.
So we don't care about the domain of interpretation.
So what it's basically saying is that in the domain, no matter what domain you use, there at least has to be one foo or human.
As long as your domain is not empty.
Which is kind of, we just know that indicates all the time.
Yes.
Okay.
We're going to assume that every interpretation, when we say it's universally valid, that means under every interpretation and every non-empty domain, it applies.
What about Japan?
Now this one also happens to work on empty domains of interpretation. We didn't use those two special rules that we want that only apply to non-empty domains.
What if it's a non-empty domain, but there are no humans?
Vacuous and true.
Oh yeah, you're right. Okay.
Oh no, you're right.
Oh,
Sorry.
No, actually, no.
Here's where we're broken.
False. That's what I'm
Yep.
saying. So,
Okay, you are right. Because yes, basically one of our premises is that
there is, yeah.
there is one of those things.
So it wouldn't work for all domains. Otherwise, one of these statements would have to be false, essentially.
Kind of what you're doing is you're making one of your premises false. We can still say our premises until our conclusion. It's just you gave me a false premise.
Okay. I think I can reason that.
So it would still be universally valid. It's stupid to talk about when you pick an interpretation that makes your premises false. So you can come up with an interpretation that makes your premises false. That doesn't matter. All that matters is if your premises are true, is the conclusion true? And that will be the case no matter how you split it, no matter how you interpret it. So yeah, I confused myself for half a second.
So in a lot of cases, we're always saying if this premise is true, then this is true. If this premise is true,
It's always an implication.
interesting. I never
Yep.
thought of it that way.
That's what we're always showing. We're showing that the premises entail the conclusion.
And it's always okay.
That's what we're always showing. So we are never saying that the premises are true. We are never saying that the conclusion is true. We are saying the premises entail the conclusion. That's what's true.
Yes.
And that's the truth that logic gets at. And that's the truth that math gets at.
Okay. Cool.
Good? All right, let's move the camera and go to our next example. Okay, we can still read it. So, here's our example, but we'll start writing over here. All right, so all mammals are animals. Some mammals are bipeds. Therefore, some animals are bipeds. All right, tell me how to symbolize it. What am I writing first? Line 1.
All x,
For all x,
if mammal applies to x, then
M applies to x implies what?
animal applies to
A
x.
applies to x. Okay? This was using rule P, and it was only dependent upon itself for its validity. All right, what's next?
There exists a mammal
There exists
for x
x. Okay, that makes sense.
such that mammal it applies to x implied or applies to x implies that biped applies to x.
No, I think it's and.
Good.
Or and.
It's and, not implies.
Not implies.
We already had this conversation, but this is one of the most common mistakes in logic, and you'll likely make it again. It's a very easy trap to fall in. This says there exists something out there such that if it's a man, then it's a biped, right? A rock would satisfy that. A rock is an object such that if it's a man, it's biped, because it's not a man.
Right.
So this accidentally includes things that you didn't mean to include. What you really wanted was that.
Yeah.
Okay. So this was our premise. Introduce only depend upon self or its validity. Okay. Alright, so we got our premises up there. Maybe scribble down what we're trying to prove. We're trying to prove some animals are bipeds. What does that mean? What does it mean to say some animals are bipeds?
There
Is
exists
animal biped?
an animal that is, or there's this X such that it's an animal and a biped.
Animal applies to X and biped applies to X. Okay. So that's what we're trying to prove. Alright. So here's what we got so far. What should we do first?
Well, we have AX. Well, we have to.
I need to specify on one of those. Do I want to universally specify on this or existentially specify on that?
The second one.
The second one. Because whatever the thing is that satisfies this is what we want to plug into this. So, 3, we now know that M applies to some beta and B applies to some beta. That was using existential specification on line 2. And it's only dependent upon 2 for its validity. Okay, now step 4 is to plug in beta into our top one. So now we're going to universally specify on line 1. So I'm going to say if beta is a man, was it man? Mammal. Then we know that beta is an animal. That is from universal specification on line 1, and it's only dependent upon 1 for its validity. Oops, 1, and that was 2. Right? Okay, now what?
Then there exists.
You're skipping a step. The whole reason we get rid of those quantifiers is so that we can start applying rule T. We can start applying our rules of logic now. So I know M applies to beta, I know B applies to beta, and I know if M applies to beta, then A applies to beta. So what do I know?
A applies to beta.
I know A applies to beta. So I know A applies to beta. And what else do I know applies to beta? That we care about. Remember where we're trying to go.
B applies to beta.
And B applies to beta. This was tautologically implied by lines 3 and 4. And so it's dependent upon both premises 1 and 2 for its validity. And now what do we do?
We make it universal or whatever the term
We
is.
universally generalize. So we say now there must exist some X out there such that X is an animal and X is a biped. Or, yeah, an animal. This was, what's it called? Existential generalization. And we did that on line 5, dependent upon 1 and 2. And we're done. We proved it. Good? All right. Let's go to a slightly more involved example now that we've done some easy ones. All Aristotle's followers like all of Aquinas' followers. None of Aristotle's followers like idealists. Aristotle does have some followers. Therefore, none of Aquinas' followers are idealists. That's what we're trying to prove. All right, so let's start by just getting our premises down, and then we'll write what we're trying to prove. So what's our first premise?
For all x, how do we want to say Aristotle's?
Let's use A for Aristotle's followers, Q for Aquinas's, and what else do we need? L for likes, and then I for idealists.
Okay.
Did we get everything we care about? I think so.
Yeah.
Okay, so for all x, what?
If A applies to
If A applies to x,
then wait.
Then Q applies to X.
No, it's you have to put like.
if you're a follower of Aristotle, then you're a follower of Aquinas.
No, you have to put like on the left.
So what do we do?
Because
Huh? Oh, you're still thinking?
If you're a follower of Aristotle, and
implies, or wait, no,
We also
should
have
put
to
another,
include
we
for
should
all
put
y,
Y in, we should put a queen in. No?
because you like all of them, and you have to imply that that you like all of them.
Okay, for all X and for all Y is what we should do, or no?
That might work. I don't know for sure though.
All right, well, we'll put the other one that you guys are talking about down here, and then maybe we'll end up using this one.
Okay,
AX is good.
then, yeah, AX.
And, oh shoot.
No,
That's not good. Don't do the and.
Okay.
Maybe it is.
Implies,
Well, okay, you could
implies
say
X,
and. You could
it
use-
implies X likes Y. Or
no, we gotta.
And Y, we have to put in that Y is Aquinas.
You also have to say and y is a what is it?
Q for
A?
Aquinas.
Yeah. Or what was it? Q?
QA,
Oh, I see.
QX,
Yeah.
QY. No? QY.
There
Yeah,
we go.
there you go.
Then it implies that they like each other.
Then x likes y.
Yep. That's what I'm thinking.
Yes, there you go. Yeah, that makes sense.
All right. That is a perfectly good way to write it. I may write it a slightly different way. There's nothing wrong with that.
You want to bring the.
I may move the for y inside.
Yeah, you can do that. That's fine.
So here's the way I may write it. For all x, if being one of Aristotle's followers applies to x, then for all y, if being Aquinas' follower applies to y, then x likes y. Maybe do a square bracket here to help see where it starts and ends. And I think that that's just going to be a little bit easier to work with. Because we can specify, get the thing, and then specify again. But what you had was perfectly valid. There's nothing wrong with it. Okay, so there's our first premise. What's our second premise?
none of Aristotle's followers like idealists. So there exists.
I would actually
No,
use
no,
it
it's
for
in
all.
Yeah, because it's none, right?
Oh yeah.
Oh.
You have to then use all
And then do a non
Negate it.
Yeah. Given that X is Aristotle's follower,
Yeah, so X, AX.
it implies that you do not like the idealists.
Not like idealists.
That's what. Well,
I as a predicate, I can't plug that into the likes.
oh, you're
Likes
right.
needs people.
We still need to specify that we're referring to idealists, or that we're referring to all idealists, which we could do. We could do it your way, which is
Yeah,
for
it's
all
almost the
y.
exact same thing. Okay, I think you see it now. For all y, if being an idealist applies to y, that implies it is not the case that x likes y.
Do we want to use a different one? Because we already used Y in the first.
No.
That's fine.
Okay.
The same way that we used x twice.
Well, it was the same X though. Well, okay, yeah. No.
I'll let it go either way you want to say it. Alright, so that's rule P, only dependent upon premise 1. This is rule P, only dependent upon premise 2.
Great.
Crush. Rule P, only dependent upon premise 2. Alright. Do we have any other premises? That was
Yes.
an awful 3. What else do we have?
Aristotle has some followers, so there exists X such that it is a follower of Aristotle.
Okay, and then let's just write, so that was rule P and only depend upon itself for its validity. And then let's just scribble somewhere what it is that we're trying to prove. So what are we trying to prove?
None of Aquinas' followers are idealists.
None of Aquinas' followers are idealists. So what are we trying to prove? None of Aquinas' followers are idealists.
X. If Aquinas' follower applies to X, then idealist does not apply to X.
Good. None of Aquinas' followers are idealists. That's what we're trying to prove. Okay. So we've got our 3 premises here. Step 4, we'll put it up here. What is step 4?
Well, if AX is, well, oh yeah, we gotta do the existential specification.
Yeah, yes.
Right, we have to specify on one of these things before we can start applying rules of logic to it.
Yeah.
And it is always a good idea, it is almost always a good idea to start by specifying your existential quantifier first. Get one of Aristotle's followers, and then you can say these things hold for that follower of Aristotle's. Okay, so first thing we're going to say is that being one of Aristotle's followers applies to beta. This is using
3.
existential.
Yeah.
I always want to write it backwards. Existential generalization on line 3, and it is only dependent upon 3 for its validity. Okay. Now, what do we know?
Existential, universal specifications.
Yeah, universally specify on both of these using beta. So now I know being Aristotle's follower applying to beta implies for all y, if being Aquinas' follower applies to y, that implies beta likes y, because I'm replacing all my x's in there with betas. And similarly for 6, being Aristotle's follower applying to beta implies for all y, being an idealist applying to y implies that it is not the case that beta likes y. This was universal specification on 1, this was universal specification on 2, this was dependent upon 1, and this was dependent upon 2. Okay, we got all that. Now what?
The conclusions are not, what's the word? Antecedent? What's the opposite of antecedent?
There's the antecedent comes at the start, the conclusion is what comes after the implication.
Okay, so both those conclusions are true.
So then we know this conclusion and we know this conclusion because we know both their premises. So I now know that for all y, Q applies to y implies if beta likes y, or that beta likes y. And I know that for all y, idealist applies to y implies that not beta likes y, right? So we know both of those. This was tautologically implied by lines 5 and 6, and it is dependent upon premises. 1, I'll just do fancy P for all our premises. Okay. Alright, so now I know this, and I know that.
Universal generalization again, or specification.
Yeah, universally specified.
Both of them. I thought it's same
Yeah, the
variable.
whole thing all in one go. And we'll replace them with the same variable in both cases.
Like that.
So then I'll say, I now know Q applies to Y implies beta likes Y, and I know that I applies to Y implies not beta likes Y. This was universal specification on line 7, and we are dependent upon premises, all of them. Now what do I know?
Beta likes Y and
What was our conclusion first? I'll try that.
Oh, we could, try to do, like, a proof by contradiction and
Or no,
just,
conditional proof probably. Just assume one of those is true.
like, assume that there is a follower of Aquinas that, is an idealist. No?
Why are we using X over there and Y over here?
Because that's the way the variables came out.
I-
Doesn't matter.
We can interchange them though?
Yes.
Okay, so
Yes.
we should assume Q is true.
So we could assume Q is true, and then it's going to take a lot of space. I'm going to rewrite it one more telling way, and hopefully we can skip that step. I'm going to write the contrapositive of this.
Oh.
Right.
What's the contrapositive of this? Not this implies not this.
Right.
So what's the negation of this?
Beta likes Y. Not Y.
This is tautologically equivalent to 7, dependent upon same premises. Alright, so I know if Q applies to Y, then this is the case. And I know if this is the case, then not I applies to Y.
And QY implies not IY.
Perfect. And you can just combine both of those together. If alpha implies beta and beta implies gamma, then alpha implies gamma is a rule of logic.
Yeah.
Combining those in one go. So we could have done what you were saying and assumed Q of Y and applied it. It just would have blown up a little bit.
Yeah, I didn't think about that. Contrapositive.
So now we know that Q of Y implies not I of Y. Okay. Now what? Oh, I guess this was tautologically equivalent to line 9, and this is dependent upon all the premises.
so now we do the ES.
Existential specification.
No, existential generalization.
Existential generalization.
Well, we just,
So what's that one again?
That's the universal quantifier.
Universal generalization.
Perfect. We're becoming more general, and we're using the universal quantifier. So this is now for all. Doesn't matter if we say X or Y. I'm just going to stick with Y.
and we can do that because they're,
They're not Greek letters. That's-
They are all variables, so they're not Greek letters. And on top of that, they weren't free variables. Remember, the only thing you have to watch out for is that they're variables and they're not free.
not.
Or not flagged, I mean. Sorry. Obviously, they were free variables up here. I meant not flagged.
Like we didn't have to, yeah,
A
okay.
flagged variable is a free variable introduced in a premise. In all our premises, all our variables were bounded. So we didn't have to worry about any flagged variables.
Okay.
If we would have done what Farley was thinking and done a conditional proof, we would have had to introduce a premise and then it would have had a flagged variable. Then we would have ultimately gotten rid of it as a premise, as an implication, and we would have gotten that same exact implication
It's true.
using rule CP.
Right.
Any questions so far? Alright, then on to the next section. What is the next section all about? It's all about the interchange of quantifiers. In other words, it tells us that if you know for all x, you have some property about x, we can replace it with, it is not the case that there exists an x that does not have that property. If everything has a property, then it is not the case that there exists something that doesn't have the property. Now, and then the other one is, if there exists something with the property, then it is not the case that everything doesn't have the property.
Right.
Now, as we introduced the existential quantifier, we actually said that this was its definition. I don't know if you remember that. We said that this was the definition of this. Now it turns out we actually don't need to specify that as the definition of this. And that our rules actually give us that fact. So this can actually just be theorems of logic, and we don't need that as a definition. You with me? So we will prove that these are in fact true as theorems of logic in chapter 5, the next chapter. So we're not going to prove them yet. For now, we're going to take them for granted. And just try and make sure that they appeal to your intuition. So we're going to symbolize two statements that hopefully it appeals to your intuition that they say the same thing, and then see how it gives us this. So this is just an example of it in progress. We're not proving it yet. We'll prove this in the next chapter. Okay. So here's two statements that hopefully, according to your intuition, say the same thing. Statement 1 says, every mathematician admires Archimedes. Statement 2 says, there is not a mathematician who does not admire Archimedes. Does it connect to your intuition how those are saying the same thing? Okay, so now we're going to write them both out and then see how this applies to them. So help me symbolize this. Every mathematician admires Archimedes.
All x, if mathematician applies to x, then admiring Archimedes applies to it.
Help me symbolize this.
There
Negation.
does not exist.
X.
What do I write first?
Negation.
Negation.
EX.
Yeah, does not exist.
Factors CX.
Mathematician, such that mathematician applies to it, and
Not X.
no.
And not what?
Does
AX.
not exist.
AX is what you said.
Such that
Oh yeah.
not AX.
It is not the case that there exists something out there that is a mathematician and doesn't admire Archimedes. You see how those are saying the same thing? Okay, now I'm going to derive this from this using these rules. You with me? Okay, so according to these rules, this is the same thing as this. So I'm going to blindly apply this without even thinking about it. So this is the same thing as this. That means that this is the same thing as, let's see, throw a negation out there. It says, instead of a for all, we're going to have a there exists. And then it says, negate whatever our inside thing is. So now I'm going to negate this. You with me? So I'm going to negate this implication.
Sometimes
I'm going to write this implication in the way that makes it easier for us to negate, which is as an or. So recall alpha implies beta is the same thing as not alpha or beta. So we're going to negate alpha implies beta. Alpha implies beta is the same thing as not alpha or beta, and we're going to negate it. You with me? And now finally, how do we negate across a disjunction?
we convert it into a junction.
You just distribute and convert your disjunction into a
And
conjunction. Yeah, an and. So when we distribute that in, the double nots go away,
then you reverse your.
the or becomes an and then we negate the a, and that gets us exactly that. See it? Okay, the whole point of that was just to see a particular example. Make it connect to your intuition and then go through thoughtlessly just applying the rule and see how it works. Okay. I don't know if we'll get to Ockham. But squiggly is in case I do and forget to move. Okay. We grab that purple marker. I think that was good. Thank you. Alright. So next, we're going to prove that there is a two-headed calf if and only if it is not the case that no calves are two-headed. I'm going to prove that there is a two-headed calf if and only it is not the case that no calves are two-headed. So first off, how do I write there is a two-headed calf? Let's just write that
There
out.
exists a calf such that it's
There exists x such that what?
it's a calf
Being a calf applies to x,
and it's two-headed.
and being two-headed applies to x. Now just mindlessly applying the rule for interchanging quantifiers, what do? I put a not, replace it with a for all, and then I not the inside. So just mindlessly following it, this tells me not for all, not c of x and t of x. Right?
Yeah.
Just blindly using the rule, not even thinking about it. Now, this is logically equivalent to distribute the not through there. So we get not for all x, not c of x, and, wait, and or not t of x. You with me? Now the last thing I'm going to do is rewrite this as an implication. So, this isn't really working as good as I thought. So remember that alpha implies beta is the same thing as not alpha or beta. So, if we switch it into an implication, negate the first thing, leave the second thing. So this is logically equivalent to not for all x. What do? We negate the first thing.
CX, isn't it?
And then switch the or with the implies, and then leave the second thing.
Implies not, yes.
Okay, and now what does this say? It says it is not the case that for all x, if it's a calf, it's not two-headed. What were we after?
Okay.
No calves are two-headed?
It is not the case that no calves are two-headed.
Right, so how would we say no calves are two-headed? No calves are two-headed would be written just like this.
Yes.
For all x, if it's a calf, it's not two-headed. So it is not the case that no calves are two-headed.
Right.
You see it?
Well, would it be implied or would it be and?
No. To say that no calves are two-headed means that if it's a calf, it's not two-headed. It doesn't mean that there's something out there that's a calf and not two-headed. It means for everything out there, if it's a calf, then it's not two-headed. Very easy to mix those two up. All right, any questions about that? We didn't go through the full proof. I was just showing you the logic for it. Just using our rules. Okay, so now let's go through full proof. If there's a federal court that will sustain the decision, then every member of the bar is wrong. Some members of the bar are right. Therefore, no federal court will sustain the decision. That's what we're proving. All right, so what's going to be...
Should we write out our symbols first before we...
Sure. If there's a federal court, we'll use F for your federal court. Sustain the decision, we'll use S. Member of the bar, we'll use B. I think that's all we need, right?
Being right.
So, let's see. Well, I'll use W for wrong, since I see wrong, not right. Oh, there's a right down there. Doesn't matter which way we go. One's a negation of the other. Okay, so we'll use those symbols. Okay, so what's our first line going to be?
There exists a federal court.
There exists asks such that federal court applies to X.
I don't know if that's a good way to go about it. I'm pretty sure it's a for all x, because we're using an implication.
No, it says if there is one.
Yeah, well, for
No,
all x,
there's
if
not.
it's a federal court, then it will sustain the
Yeah,
decision.
Let's write what he's saying so that we can look at both of them, see which one makes sense. So you're saying start it like this, right?
Yeah.
This saying there is something that's a federal court. This saying everything is a federal court.
Implies
Implies Were we doing implies up here?
Yes.
Yeah.
Implies.
Implies sustain SX.
Yeah.
And then
For
that
both
whole
of them.
thing needs to imply BX. Bar is wrong.
Well,
Oh, it's an and. It's a federal court and it will sustain the decision.
Oh, yeah.
Okay.
And then it implies every member of the bar is wrong.
Yes.
So,
Yes.
and, now what were we writing?
We also have to say,
Implies.
we have to use for all member of the court. Or for all y, given that y is a member of the court, or something like that.
Yeah, implies all Y. Such that
Y is in the
Y
bar.
is wrong.
Something like that.
No, I don't know.
Y is member of the bar. You have to put
If there's a federal court that will sustain the decision, then every member of the bar is wrong.
right. So if it's a member of the bar, then it's wrong.
So maybe let's just take this one step at a time. Let's write out there is a federal court that will sustain the decision. How do I write that?
EX such that FX implies.
So that's already this, right?
Yeah, implies.
If we were to put our parenthesis right there. That says there exists something out there that's a federal court and will sustain the decision.
Yeah, right.
So if there's a federal court that will sustain the decision, then what?
Well, now you're talking about implication.
Now we're talking about an implication. Well, do I want to do it that way? So here's the way I'm thinking about it, is putting it outside the quantifiers altogether, rather than having this inside the existential quantifier. See what I'm saying?
Yeah.
Then for all y, what are we saying about y?
That it's a member of the bar, right?
That being a member of the bar
Implies
Implies it's
wrong.
wrong.
implies it's wrong. Okay, I like that. That's how I will write it. If there exists something out there that's a federal court and sustains a decision, then for all y, if it's a member of the bar, then it's wrong.
Mhm.
Okay, so now 2.
There exists a Y.
Such that it's a member of the bar, right? So
Yeah, such that it's a member of the bar.
and it's not
Wrong.
wrong.
I like it.
Yeah.
So let's just quickly say this was P dependent upon 1. This was P dependent upon 2. Alright. Okay, now what?
Now we're trying.
Maybe let's scribble out what we're trying to show. What are we trying to show?
That no federal court will sustain the decision.
Agreed, but now tell me what to write.
No FX or negation of F. Oh.
No. For all x, no. There's like no negation.
I don't know how to write. Oh, for all x, negation.
FX.
For all x, if it's not a federal court.
No.
No.
So if it is a federal court.
If it is a federal court, then what?
It will not sustain.
Not sustain the decision. There we go. No federal court will sustain the decision. For all x, if it's a federal court, it will not sustain the decision. We like it?
Mm-hmm.
Alright, I like it too. Okay, so now here's our premises. That's what we're trying to prove. Now, what to do, what to do.
We undo our E's.
We could, but that is going to make headache for us. Odds are that if we're given this problem in the chapter called Interchange of Quantifiers, we're going to want to interchange our quantifiers.
Probably.
So I would not go about existentially specifying yet. Although you could. I just think it's going to create a lot of extra work for us.
So we kind of have an E of X, P of X there. Yeah, so we could say that implies, not A of X, or not of,
Not for all. Let's keep it Y since we're using Y, but I'm with you.
not for all, and then the negation of P. So not B of Y, and
It would be B of Y.
Or, if we're going to negate it.
W of Y.
W.
Oh wait, no, no, no.
Good?
Yes.
Okay. This is tautologically equivalent to line 2, and it is only dependent upon 2 for its validity.
Yeah.
Nice. I like where we almost are. I want to get it into some nice form such that we can use it with this. What do I wish this was?
Implication.
Just, I mean, you wish the knots were gone. Oh, you could negate it? Oh.
No.
Is this common trick here is to think, does this somehow resemble this side of the implication? Not really. Does it somehow resemble this side of the equation?
Yes, it does.
Yes. How is it different? Like, what's your gut telling you?
There's the two negations
And there's the or instead of the
and the or instead of the
implication.
implies, so we can do.
So let's replace the or with the implies really quick, and maybe that will help. So not for all y. How do we replace or with an implication? You negate the first one and leave the second.
So by implies wi.
Okay, this is tautologically equivalent to line 3. Still just dependent upon 2. Okay, now how does that compare with that?
It's
It
the
has a
negation of
negation.
it.
It's the exact negation. So this is alpha implies beta. This is
Not beta.
not beta. And so we can conclude,
Alpha has to be true.
what?
Beta implies
Not
The
alpha.
antecedent has to be true.
Not alpha.
You
Yeah.
can't.
If alpha implies beta,
Not.
not beta implies not alpha.
Right.
That's just.
Contrapositive.
Or that's.
So I have not beta.
Yeah.
So this and this together help me conclude.
Not.
That
Not
does
alpha.
exist. Yeah.
Is everyone seeing that okay?
Yeah.
That's kind of a big jump in logic.
No, that makes sense.
Alpha implies beta, therefore not beta implies not alpha. So we know not beta implies not alpha, and we have not beta.
So not.
So we can conclude not whatever that is. So we can conclude not alpha. Sorry, I don't know why I put parentheses there. There's nothing wrong with functional notation, but this is tautologically implied by lines 1 and 4. And now we are dependent upon all our premises. Right?
Right.
Okay. Now it's not quite what we're after. What are we trying to state? We're trying to state this. And instead we have that.
Interchange the quantifier.
Let's interchange the quantifier. Which would be the easiest way? Let's just blindly do it. I'm just going to try and be clever, but it's too much in one go. So let's just blindly do it. I'm going to replace the there exists. So we're using this one right here, right? So what do I do first? I pull a not, but we already have a not, so it's going to cancel that
So
out.
it's gonna be
For all.
So we're going to jump straight to the for all x. And then we need the negation of whatever's inside of here. So how do I negate
No.
alpha and beta?
Not fx
Not alpha
or
or
not s.
not beta. Everyone understanding that okay?
I remember that. Okay.
And now we could apply a negation.
So this
or
is
implication.
tautologically equivalent to line 5. And we're still dependent upon all our premises for our validity. Right? Okay, now what was your idea?
Apply an implication to not fx or.
Yeah, switch the or for an implication. How do we switch an or for an implication?
For all ax.
We just negate the first part.
Yep.
So then it becomes fx implies not sx. And that is tautologically equivalent to 6. We are dependent upon all of our premises. And now, that's exactly what we were after. Dun, 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 dun. questions with that one? Cool. Okay. The last section of this chapter is just called general inference. And all it introduces now are a bunch of restrictions to these rules. So far, we can't just use the rules exactly as they're stated. There are some exceptions. We didn't state the exceptions when we gave you the rules for two reasons. One, the rules are confusing until you already get comfortable with proof. And two, your intuition automatically stops you from breaking the rules 99% of the time. So even if you didn't know what the restrictions were, chances are you would stop yourself from violating them. So this is just to make it explicit. Odds are you wouldn't have ever actually tried to break one of these. And notice that we've done all these proofs we've done, and we've never once violated one of these. But let's go over what the restrictions are. So our first restriction is that we cannot existentially generalize to a free variable in our formula. Let me give you an example, and then when you see the example, you'll say adopt. So let's start out with this statement. For all x, there exists a y such that x is less than y. I'm intentionally giving you a true statement in arithmetic. For all x, there exists a y such that x is less than y. Or in other words, pick any number you want, I can always find a number bigger. That's all it says. With me so far? Mm-hmm. Now if we universally specify, we can replace x with just some free variable x now. So there exists a y such that y is bigger than x, whatever x is. You with me? Now we can existentially specify, and we can call whatever that y is alpha. So alpha is greater than x. So far we're fine. But now if I say, okay, so then there exists an x such that x is less than x, I replace alpha with a free variable in my expression. Now we got nonsense. So red is when we use bad logic. Can't do that. So I can't existentially generalize to a free variable in my formula. X is a free variable in my formula. I can't replace my alpha with an x. Otherwise, we can prove nonsense. Does the first restriction make sense?
So you can't generalize either way. Free variable is what you're basically saying. Whether we're doing existential generalization or universal generalization, we cannot do either of those to a free variable.
We can't do existential generalization. What's the other one you said?
Universal generalization.
Every time we universally generalize, it's not a free variable. We did that 100 times.
Right.
Okay, next one. We cannot existentially generalize or universally generalize in an order that swaps quantifiers. And the way I always think about this is like parentheses. So first, let me show you an example of it, and I'll tell you what I mean by think about like parentheses. Let's look at this statement. For all x, there exists a y such that x is less than y. Or in other words, for every x, there exists a y where y is bigger than x. Same statement. This is true. Universally specify, that means there exists a y such that y is bigger than x, whatever the x is. Existentially generalize, that now gives us that x is less than alpha for some alpha. Now, if I universally specify here, that gives me for all x, x is less than alpha. And then if I existentially generalize on that, I get that there exists a y such that for all x, x is less than y. And so what I essentially did in that whole process was swap my quantifiers. Which you can't ever do. And so I say, think about this like parentheses. So if I have some open bracket here in an expression and I'm going along, and then I have some open parenthesis and I'm going along, I have to close out this parenthesis before it's possible for me to close out this bracket. I eventually have to have a closed parenthesis before I can have the closed bracket. So think about when you specify, it's opening a parenthesis, and when you generalize, it's closing it. So here's where I universally specify. Here's where I existentially specify. I have to existentially generalize before I universally generalize.
How do you keep track of that?
There's notation for doing it in terms of keeping track of subscripts, and it just typically makes a mess of the proof. So there is a notation to do it. It's just so heavy-handed for something that people, just following their intuition, almost never do. So, since right here, since we universally specified, then we existentially specified, first we have to existentially generalize before we can universally generalize. And so it always has to create this sandwiching thing. Does it make sense what I mean with like the parentheses? Okay. Next one. You cannot universally specify to a bound term. What do we mean? If I know that for all x there exists a y such that x is less than y, I can't universally specify and replace that x there with a y. Because a y was already a bound term in my formula. Again, you would have never tried to do that, but okay, we have it explicit. You can't do that. Make sense? And then finally our last one. We cannot existentially generalize to a bound term. What do we mean by that one? So here's an example. There exists an x such that for all y, x plus y equals y. That's true. That special x is 0. There exists an x, namely 0, such that for all y, x plus y equals y. That special x is 0. From that, we could conclude that for all y, alpha plus y equals y, where alpha is a stand-in for whatever that x is. We know it's 0, but let's pretend secretly we didn't know what the x's name was. So here to here, we're still good. What I cannot do now is existentially generalize to a bound variable in my expression. Y is bound here, so I cannot existentially generalize and say now there exists a y such that for all y, y plus y is equal to y. Now it's just nonsense.
Right.
Good? Alright. Now these other ones are just examples, and then no new theory. We'll start the next theory next time, so we'll just go through some examples. See ya. Alright. Here's kind of a tight, hard proof. All horses are animals. Therefore, all heads of horses are heads of animals. What's our premise? All horses are animals. That's pretty straightforward. How do I write all horses are animals?
For all x,
For all
horse is x.
For all x, if horse applies to x, then animal applies to x.
Oh.
All horses are animals. What on earth are we trying to prove? All heads of horses are heads of animals. How do I write that?
For all x, given that, well,
For all x,
we given that x is a, okay, they're all heads of horses are heads of animals. It's almost like you're saying the same thing in premise 1, but you're somehow also implying that x is I don't know.
yes, this is kind of hard to think about. All heads of horses are heads of animals.
Well, you have to assume that horses have heads.
We don't have to assume that horses have heads.
Are we also
We just have to assume that if something's the head of a horse, it's the head of an animal.
Okay.
that all animals have heads? This is what we
And we don't actually even have to assume that. We're going to prove it. All we have to assume is that all horses are animals. And this is going to follow from that one statement. If all horses are animals, then it's for sure the case that the heads of all horses are heads of all animals. That's something that's obvious to our logic, but it's shockingly hard to think about what we're trying to show.
It's true. It is. It's not very intuitive.
So, therefore, all heads of horses are heads of animals. So for all x, we'll think about x here as being our heads. For every head, what?
What? Okay, if that's the case, the premise 1, oh, that's right, they're not related. Okay,
Okay, yeah, it doesn't matter.
I forgot. Okay, yeah.
Alright, we'll put a y here. For all heads, what? Let's think about the quantifier applying to the heads, and that's going to make this easier.
Well, yeah, just h of y, right? Isn't that?
If the head is a horse, well, we know that's not true because it's a head.
Well, what symbol are we using for head?
We can use T for top.
Okay.
What does it mean for y to be the head of a
It just
horse?
seems like it's exactly the same as the first premise.
What does it mean for y to be the head of a horse? Trying to think about how we can say y is the head of a horse.
Well, you could say where y is the head of a horse.
How would I say that?
Some premise that makes it a head of a horse. It'd have to be its own. Oh, well, are you applying two premises on top of each other?
Let's take a
It's called a
step.
head.
Let me see if I can.
Oh, it's a horse and it's a head.
No, it can't be a horse and a head.
Dang it.
Heads aren't horses.
That's right, you're right.
So let me try and help you easier. Help me write out the statement that Parley is the son of a man. How would I write Parley is the son of a man? Or there's something out there whose name is Parley. Well, no, we'll say that. Parley is the son of a man. How would I write that?
You start out just saying where x is a head. That's not,
What does it mean that you're a son of a man?
I don't know.
It means that there exists something out there such that,
It's you.
no.
No?
So Parley is now a constant p. We have p for Parley. Talking about Parley specifically. We're saying Parley is the son of a
Applies
man.
to X.
There exists something out there such that
Son applies to it and man applies to it.
they're a man, and what? Son is a relation between two things. And Parley is the son of X. That's what it means to say that Parley is the son of a man.
Oh, it's a relation?
There exists something out there such that they're a man, and Parley is the son of the man. Okay, so now for all y, I need to say, if y is the head of a horse, then it's the head of an animal. How do I say y is the head of a horse?
Well, we first have to specify that.
So y h x?
Well, okay,
Yes,
is the
sir.
horse a constant?
For all y,
Okay, we're not talking about a constant here in this case. So we do need to do, for all y, it does make sense, we need to specify that it is a head, that y has to be a head, don't we?
did we have to specify that Parley? All right, you guys have struggled enough. There exists something out there such that that thing is a horse, and y is the top of it. Or in other words, y is its head. So this is for all y, so far, there exists something such that it's a horse, and y is the head of it. Implies what? Should have written this further to the left. We're going to run out of space. Keep thinking, and I'm going to rewrite what we had there. So we're trying to show that for all y, remember y is going to be the standard for the head.
Well, I kind of just need to digest what you've written.
If there exists something out there such that it's a horse, and y is the top of it, then what? So if there exists something out there, if there exists a horse that y is the head of, then
There exists an animal.
there exists an animal. So there exists x such that animal applies to x. And what?
That y is the top of.
And y is the top of it. And then close off right here. So we're looping over all heads.
I just,
And we're saying if there exists something in the universe that's a horse and y is the top of it, then there exists something in the universe that's an animal and y is the top of it. All heads of horses are also heads of animals. If y is the head of a horse, then y is the head of an animal. If there exists a horse out there such that y is the head of it, then there exists an animal out there such that y is the head of it. Click it.
And we're doing T for what?
T is top of. Y is the top of x means y is the head of x. Since we used h for horse.
Oh, yeah.
Good?
It's just the use of the relation in that is a little,
For the top of?
I just never really think of it that way, but, no, I mean, I can see that it needs to be a relation, but it's just, I'm
Yeah,
never-
that's what it means to say that something's ahead of a horse. It's a relationship between an object and another object.
Yeah,
To say that this thing is my head is to state a relationship between this thing and me.
it would have to be a relationship, as for some reason that's new to me.
Okay, so we're good with that, right? Here's what we're trying to prove. Okay, and I think that that's the hard part. So, understanding this is what we're trying to prove, let's go from there. So here we have our first premise, P, and it is only dependent upon itself for its validity. Let me shove my camera a little bit so that we can scoot over there as needed. All right. So now we're trying to prove this. How would we attempt proving that? I mean, ultimately, that's one humongous implication, right?
Well, with the
It's,
universal,
yeah, but
okay.
almost all our implications are encoded in universal quantifiers when they're in premises or conclusions.
That's a good point.
So it's some big implication. What's our standard procedure for proving an implication?
Oh, conditional proof?
Yeah, assume the antecedent and show that implies a conclusion. So now I'm going to assume that this is the case and show that implies this is the case.
Do we need to remove the all y first to apply that reasoning?
Well, let me just flat out write out what we're going to assume. So we're going to take as a conditional premise there exists an x such that h applies to x and y is the top of x. Right? So we just added that as a premise. We need to get rid of that as a premise before everything's all said and done. And now we have a flagged variable y in our premise. So this is dependent upon 2 with flagged variable y. Right? We've done this 100 times. You've seen we started out with something for all x. If p applies to x, then q applies to x, and we started out with okay, let's take it as conditional p of x and go from there. And x was a flagged variable. We've done that 100 times. It's the exact same thing. It's just a slightly more convoluted thing than that.
I'm just curious if you're jumping multiple steps to accomplish that.
No, so far haven't done any jumping. Just 2 flat out using the rules directly. Okay. So now 3. That marker's not any better. Stick with black, I guess. 3. Now what do we do if we take that as a premise?
We could do, I kind of want to do negate interchange, but.
We're no longer in that chapter, if that helps give you a hint. And so, the right approach here is a straightforward approach.
Fine, if we. Then
Let's
take the-
existentially specify.
Yeah, existentially.
Right. So if there exists some x, such that it's a horse, and y is the top of it, then that means, let's call some, one of those things we'll call beta. Then there's some beta such that beta is a horse, and y is the top of beta. Okay, that was existential specification on line 2, and dependent upon 2y for its validity. Okay, now what?
We could also do a universal specification on premise 1.
Perfect. That's exactly right. So now, for line 4 here, we're going to write H beta implies A beta, this was universal specification on line 1, and it is only dependent upon 1 for its validity. And now,
If HB is true, which is then AB is true.
so what can I write here as line 5?
If H beta is true, well, A beta.
I can write A beta. And what else can I write?
Wants to write.
Notice what we're trying to show. We're trying to show this implies this.
I'm just solving things as I see them. Okay, let's see. Oh, well, we can also put and y.
And perfect. And y is the top of beta. Right? So this was just tautologically implied by lines 3 and 4. And now we are dependent upon 1 and 2 with flag variable y. Good? Okay. For line 6, we'll write that up here. For line 6, what should I do now? So I've got this. What am I trying to get? I'm trying to get something that looks like this.
Okay, well, we have the internal, I think, well, well, we need to, universal, or existential universal, or existentially general?
Perfect.
Okay,
There exists x such that
generalize.
animal is in x and y is the top of x. If I know beta is an animal and y is the top of beta, then I know there exists something out there that's an animal and y is the top of it. So that was existential generalization on line 5. And we are still dependent upon premises 1 and 2 with flag variable y. Okay. So now, 7, what can we do?
Well,
Felt like you were right about to say it.
well, it's a conditional premise.
Yeah, rule CP. We showed that if this is the case, then this is the case. Therefore, this implies this. So I just really showed that if we know that there exists an x such that being a horse applies to x and y is the top of x, then there exists an x such that x is an animal and y is the top of x. That is using rule CP from lines 2 to 6. And now we are no longer dependent upon 2 as a premise. And so our only premises now are 1. And we no longer have a flag variable. And since we don't have a flag variable, we're allowed to
universally generalized.
universally generalize. So now I can say 8 and universally generalize. And now I can say for all y, if there exists an x such that x is a horse and y is the top of x, then there exists an x such that x is an animal and y is the top of x. And that was using universal generalization on line 7. And we are still only dependent upon 1 for our validity. And we're done.
Okay.
Good?
Yeah.
Okay. I don't know. We have time to fly through this last one? None of Ockham's followers like any realists. None of Ockham's followers like any realists. So what does that mean? That means for all x, if being one of Ockham's follower applies to x, then that means for all y, if y is a realist, I'll use capital R for realist, then is it that they do like or don't like? None. Then not likes applies, then it is not the case that x likes y. Put a square bracket here to help us read this. For all x, if you are one of Ockham's followers, then for all y, if y is a realist, x does not like y. None of Occam's followers like any realists. With me?
Could you symbolize? It just took me. Okay, yeah, that makes sense.
For all x, if you're one of Occam's followers, then for all y, if y is a realist, x doesn't like him.
Yes.
None of Occam's followers like any realists. All right, next one says, any of Occam's followers like at least one of Hobbes' followers. Any of Occam's followers like at least one of Hobbes' followers. So for all x, if you are one of Occam's followers, what does that mean?
That you like.
There must exist some y such that, like at least one of Hobbes' followers, so such that being one of Hobbes' followers applies to y, and x likes y. That's premise, only dependent upon 2. So, for all x, if it's one of Occam's followers, then there must exist some y such that y is one of Hobbes' followers, and x likes y. Any of Occam's followers likes at least one of Hobbes' followers. Finally, Ockham has followers. So 3, there exists an x such that they are a follower of Occam's. That again was a premise, only dependent upon itself. Oops, 3. Good so far?
Yep.
Okay. Therefore, some of Hobbes' followers are not realists. Some of Hobbes' followers are not realists. Let's write that out. That means that there exists an x such that x is a follower of Hobbes and not a realist applies to x. Some of Hobbes' followers are not realists. There exists someone out there who is one of Hobbes' followers and they're not a realist. That make sense? Maybe put red box around what we're trying to prove so we don't think it's part of that proof. Okay, that's what we're trying to get. Now, step 1 is, I'm going to existentially specify on that. Pretty standard first step. I think it's the first step. Not seeing ahead on this one. So, O applies to beta. That is just existential specification on line 3. And only dependent upon 3 for its validity. Okay, now, both these are true for all x, and so it's true for this beta guy. So I know that if beta is one of Occam's followers, then this is true for beta, and if beta is one of Occam's followers, then this is true for beta. Now I'm going to skip straight to writing this line and this line. Doing a bunch of logic in one go. Tell me if I'm losing you. So I'm going to go straight to, for all y, if they're a realist, that implies that beta, that implies not, beta likes y. And 6, I'm going to say for all y, there exists a y. There exists a y such that y is one of Hobbes' followers and beta likes y. You see how we could get this from this and this? So universally specify on that, replacing your x's with beta, and then combine that with that. And so I'm going to say, we're doing a lot in one go. But essentially, these are tautologically implied by 1 and by 2, just to make sure we're tracking the premises. So this is dependent upon 1, this is dependent upon 2. Oh, and it's also using beta 3 there. So 1 and 3. This is using 2 and 3. So this is dependent upon premise 1 and 3. This is dependent upon premise 2 and 3. Okay, so now I've got those two things. Now, where are we trying to get? We're trying to get here. So what can I do next? Maybe focus on 6 for a second. This says that there exists something out there such that it's a follower of Hobbes, and beta likes him. Remember, beta is one of Occam's followers.
Well, we could do a existential specifications.
Perfect. Again, and just give it some other
We
name.
could also do it for both. Also the universal specification as well.
So yeah, we'll start with this one. So we can say H applies to, what symbol should I use?
I don't know, alpha?
Alpha. Alpha, and beta likes alpha. So this is universally specifying on, or existentially specifying on that, right?
Yeah.
And now I'm going to universally specify on this using the same alpha.
Yes.
Since this is true for any y, it's true for whoever that alpha guy is. So I'm just going to end that here in case we're running out of vertical space. I'll put enough space that we can kind of say that they came from two different lines. So writing this here, universally specifying with alpha. So alpha is a realist, implies it is not the case that beta likes alpha. Sorry, that's an alpha there. Okay. This was tautologically implied by lines 5 and 6. Or actually, it was universal specification on, but who cares? 5 and 6 is now using all our premises, so fancy P for all our premises.
Yeah.
Okay, so now, remember, I'm trying to get something as Hobbes' follower and not a realist. I have the Hobbes there. I need not a realist. Alpha being a realist implies beta doesn't like alpha. But we know,
Oh, so yeah, therefore R, not Rx.
yeah.
Or not RA.
Not our.
Alpha.
So alpha being a realist means beta doesn't like him. But we know beta likes him.
So there has to be not.
So then they're not a realist.
Yeah.
So I can put 8 here. Then we know that alpha is one of Hobbes' followers, and not being a realist applies to alpha. This was tautologically implied by line 7, still dependent upon all the premises. Okay, now what can we do?
Now we can just essentially generalize.
Perfect. So now 9, we can finally write there exists an x such that h of x and not r of x. Universal generalization on line 8, dependent upon all our premises. Ka-ching. Whew, we were able to get done time. Sorry, kind of rushed you on that one. I didn't know how long it would take.
No, that's fine. I was, yeah, able to keep up. It would take me a while to get those first two premises figured out.
Okay, sorry. But there we go. That ends this chapter. So next chapter, we will be introducing identity, the equal symbol, and we will start proving theorems in logic now, rather than just proving arbitrary statements. Any questions for what you want recorded?
This is basically all of the rules and everything.
We now have all the rules of first order logic. When I told you at the start of the course what we're doing, I said we are doing, to be verbose with the name, we are doing propositional and first order predicate logic. That's usually what most people mean with first order logic. And logic with identity. So we still need to introduce identity in our rules for working with identity. But in terms of first order logic, these are all the rules. We've covered them all.
Gotcha.
And in fact, you don't really need reductio ad absurdum. That's one that can be proven. So your actual hard fast rules are rule P, rule T, rule CP.
Why would you actually need CP2? Because you could prove that using...
No, you use CP to prove RA, but you need CP. It's one that enables you to get rid of your premises.
Oh, that's right, that's right.
Okay, so, and then you have your 2 rules for dealing with your universal quantifier and your 2 rules for dealing with your existential quantifier. So at the end of the day, there's only 7 real rules. We use 8 because reductio ad absurdum is really useful.
Gotcha.
So yeah, those are all the rules. Identity, there's 2 rules for working with identity that we'll have. And those 2 rules are basically everything's identical with itself, and equals can be substituted for equals. That's pretty much what the rules are. And then those are all the rules for a full-blown logic with identity.
Cool.
And then we're ready to get into an actual axiomatic system. We'll do examples with axiomatic systems.
Okay.
Any other questions? Cool. See you guys next week.
Not